Now that the recording's on progress, yeah, welcome everybody. Thanks for coming and take it away.
Yeah, thanks so much. Thanks, Mark, for this short introduction. Thanks, Mark, for inviting me here. I'm really very glad. It's my first time in Michigan. I've been to Chicago, but it's Illinois, right? Because you can stay in this area, but I've never been here. So far, I really like it here. Thanks for.
Statistically meaningful in the college, electoral college.
Okay. Yeah, thanks so much. So my talk will be it's a math department, so I'll try to be mathematical. At the same time, there are some kind of applications that I have behind it, so there will be no experiments. Like it's a still theoretical talk. It's based on two papers. One is with Pedro Abdallah, who was a PhD student back then at ETH Zurich. Now he's working actually with Roman Grshin, whom we already mentioned today, at UC Irvine. It was recently accepted to the journal. And there is a kind of a follow-up paper related with Arshak Minasyan, who is an assistant professor in Paris. Okay, here is the problem. So I'll just, maybe I should remove this. I'm not hearing anything. Okay, cool. So I'll study the problem of covariance estimation first. So I have a set of ideal random vectors in RD with some covariance matrix sigma, and I want to estimate the sigma. So sigma is a known. So what are the applications we have in mind? Applications are principal component analysis, least squares, and people care about it in geometry. How we measure the quality of estimation. So to measure the quality of estimation, we will use the operator norm. So I want to construct the matrix sigma such that it's as close as possible an operator norm to the true matrix. And then if you write it down, this is a supremum over all directions in the sphere between this quadratic form and this quadratic form. There's like values of the x, right? So my focus is on the non-asymptotic analysis, and I really care about the explicit dependencies on parameters. So it will be non-asymptotic bounds. And I will also mention advanced for those who are interested in open problems or maybe more on the applied side. I will care about the information theoretic rates. So I will not provide you any computational method, unfortunately. So it's a big open question. It's a big open question for me, but in general, we really struggle in many cases on how to estimate certain matrices like efficiently, at least in the setups I'm considering.
Can I ask you a simple question?
Yes.
Yeah. Go back to what it is. Maybe I'm missing something, but you say operator norm. That's how you measure the. So isn't it enough to multiply from the right by d?
Yeah, because it's a symmetric matrix. So right, you just yeah. So it's I'll put some PSD metric. So it's also PSD. So the largest singular value will be equal to the supremum over all directions. The direction v is the same on the left and on the right. Yeah. So it's just like falls from Roman. We can check it in Roman version.
Okay.
Yeah, in general, of course, it's not like it's not non-symmetric, then you have to be more careful with two directions, right? Okay, good. So what we know about it? So we know something about the so-called sub-Gaussian random vectors. So if I have an ID sample of so-called sub-Gaussian random vectors, so think of Gaussian if you want, then the following holds. So it's a simple result. Then the operator norm of the difference between the sample covariance matrix, normalized by n, and the true covariance matrix is less or equal. So this symbol means that I ignore the multiplicity of absolute constant factors. Largest eigenvalues square root dimension of the vectors divided by the sample size. And this holds with high probability. So probability 1 minus exponent minus d, whenever n, the sample size, is large enough. So n is larger, greater or equal than d. Now, what is the problem with this result? It doesn't work in high dimensions, right? You need dimension d to be smaller than the number of observations. So it doesn't work for in full generality. It works only when when n is large. So then we define the so-called effective rank. And the effective rank of the covariance matrix is the following. So this is the ratio between the sum of all eigenvalues and the largest eigenvalue, right? So you might have a certain, I don't know if it's visible here, a certain decay of eigenvalues. This will be the largest, number one, and then it goes all the way down. So you have a highly decreasing pattern of eigenvalues, and then this quantity can be actually quite small, right? The sum of eigenvalues will be relatively small compared to the largest. So in general, the effective rank is always less or equal than dimension, and you can generalize it to Hilbert space or general Banach spaces. The effective rank can be small. So now the result of Kolchinsky and Karim-Munisi from 2017 tells us the following, that if I compute the sample covariance matrix in the Gaussian case, according to this formula, and compare it with the true covariance, then I can get a bound written in terms of the effective rank. So if you look at this formula now, then there is no dimension anywhere. So D that I had before is now replaced by R, which is the ratio between the sum of eigenvalues and the largest eigenvalue. And this works whenever n is larger than the effective rank, right? So I have n that can be, like the dimension can be very large, but n is only required to be larger than the ratio between the sum of eigenvalues and the largest eigenvalue. So the proof of this result is based on Telegrand's famous generic chaining machinery, and it's really specific to the sub-Gaussian assumption. So if you, for example, have sub-exponential vectors, then the same proof wouldn't work, but at least we don't know how to make it immediate. And another thing, some people in the room are interested in this so-called matrix concentration inequalities. Unfortunately, matrix concentration also doesn't work here directly. So you cannot use, for example, any bounds from Joel Traub's book to recover directly this result. So it's a very specific, hard, if you think of it, hard machinery result that requires the sub-Gaussianity or Gaussianity.
Yeah. Please go back to the previous one. So the trace.
Yeah, so it was dimension here in the red one, and dimension again. It's I don't want to pay dimension in high dimensions, right? Like if I have the real world data, it's more likely not isotropic. There is a motivation to study these effective ranks. So I have a decay of eigenvalues. And if I have a decay of eigenvalues, then this quantity can be much smaller because it's a sum of eigenvalues. So if I have a certain polynomial decay of eigenvalues, this trace will be much smaller than the largest eigenvalue times the dimension. So the importance of the result is that you replace the dimension by the effective rank, though again, the proof, mathematically, the proof is quite hard. Okay, so that's what I want to mention now. So those who are familiar with theory of random matrices should be familiar, could be familiar with this famous buy-in asymptotic result. Like the bound before, if I'm scrolling through to the previous slide, this is a non-asymptotic bound, which means that it holds for all sample sizes, right? For the distributions, we may think of n being equal to 50, and then inequality will hold. Now, the asymptotic results are more classical to probability and statistics in some sense. They are saying what happens when something goes to infinity. So in buy-in, prove that essentially the following limiting statement. I'm slightly vague here because I write explicitly the dimension of the sample size, but of course the dimension of the sample size for me is equally beta. So to make it like fully mathematically rigorous, you have to work a little bit, but you understand what's going on, right? Dimension and the sample size simultaneously go to infinity and approach some constant beta, and then the limit here will be essentially 2 square root beta plus beta as both n and d go to infinity. Now, what is important here is that, so the weakness of the result in some sense is that it requires that the vectors have IED coordinates, or independent coordinates, which is again not the thing we have for real value data. But the nice thing is that we only require 4 moments. So the previous theorem, non-asymptotic, required the Gaussianity, and here I only require 4 moments, right? There is some gap between the number of moments I need for these results, right? So that's kind of the indication that something can be improved here. And let's take a look again at this Kolchinsky-Vanisi bound, and let's take a careful look at the expression. So if you think of it, then on the right-hand side, right, I have on the left-hand side, I have something that change or measures the deviations of some quantity which corresponds to the second moment around its expectation, right? So what is the typical deviation of, or how do we write down the deviation of random variables, right? Usually we use some kind of Chebyshev's inequality for a single random variable, and we use the variance of the random variable. So if the random variable itself is the variance, then the Chebyshev will be written in terms of the fourth moment, right? So something about the fourth moment should appear. But if you look at the right-hand side of this, all the information about this bound is only written in terms of the first 2 moments, because effective rank and sigma is just only incorporates the first 2 moments. So again, the general principle is that we would expect to see something that depends on the fourth moment of the Gaussian here, but you see, if you look at the formula, we only see the second moment. So therefore, the idea will be to introduce some kind of a necessary, almost necessary assumption related or called the hypercontractivity. Let's think of it. So I'm saying that there is a LP-L2 hypercontractivity for the distribution if the following holds. So assume that I have a zero mean random vector in RD, and I fix some moment P, which is at least a fourth point. And then what I want to do, I want to compare the higher moments of the projections, like X times V. So I project my random vector onto the direction, and then I compare the LQ moment, right, of a higher moment, and I want to assume that the higher moment can be controlled in terms of the second moment.
But if this holds for Q equal to P holds for Q.
Yeah, so what is important, it's true. What is important, yeah, I just want to this explicit function here, because the like cap of Q, like it clearly hold, like the hard, it is hard for this to hold when Q is equal to 4, but then, or like higher or higher powers, but then as a function of Q, it will be, the constant will be larger, right? So I want to have an explicit dependence on Q. But yeah, Mark, you're right. Anyway, I want some distribution whose higher moments can be controlled by a few higher moments, can be controlled by lower moments. Gaussian is such an example, right? If you go to, say, any book or you check it in Wikipedia, then the moment number 11 of Gaussian random variable can be written as a formula only in terms of mean and variance, right? That's kind of 2 moments define everything. So here's like a more general principle in higher dimensions. Few moments define everything. And then I would go, kind of, we define at least four moments that maybe, maybe the Q or P will be larger. Maybe I'll just assume 8 moments or 11 moments in the end. Is it clear about the definition? It's like a hypercontractive.
Where T, Y, where T appeared in that inequality.
Yeah, so P is the kind of the largest power. For example, imagine that I have, like, P is, say, 11, right? So I'm saying that the 11th moment is controlled by the second moment. But why I put this Q here is I want to, kind of the lower the moment Q here, it's for all smaller Qs also. The lower the moment Q here, the better this constant is, right? Like when Q is equal to 2, this is 1, so I'll need this exact dependence later in the bound. In any case, for simplicity, you may think of it just Q equals to P, and then there is some constant, but again, how this constant depends on Q is important for my derivation later.
But I had some P related quantities that appear in that specifically in that inequality, right?
Yeah, but I said that for all Qs, right? So we have V and all Qs between 2. So P is the largest moment until I care, then maybe P is 11. Yeah. Thanks for these questions.
Q, that's it. P equals Q.
Yeah, that's it. Okay, so now I put this hypercontractivity, and hypercontractivity is the generalization of Gaussianity. It's weaker, right? Because I only look at the first moments. I don't care about higher moments. The second thing that will make my problem hard is to make the adversarial contamination. What does it mean? So I'm not observing actually the data x1, etc., xn, but I'm observing an epsilon contaminated sample, which consists of like x1 tilde, xn tilde, right? Like there are different vectors. Now, what is my contamination model? And the contamination model is as follows: that after the true sample is generated from this, like my distribution, there is an adversary who knows my estimator, knows everything, and this adversary just replaces an epsilon fraction of my vectors by anything they want. Like they kind of just take a fraction and replace by the most adversarial examples I can possibly imagine. They complete adversarial for us. So the only hope is that the fraction is relatively small. For example, 1% of points is contaminated by the adversary. The remaining 99% are coming from the original distribution. And for those who are familiar with robust statistics, this model is more general, the so-called Huber's epsilon contamination model, introduced like in 60s and 70s. This is one of the most general models of contamination people study in the literature. And the question I'm asking is the following: can we estimate the covariance matrix, like sigma in operator norm, based on the contaminated sample, epsilon contaminated sample, for the distribution that only satisfies this hypercontractivity? So I don't have Gaussian, I have hypercontractivity, and I don't have a clean sample, I have a contaminated sample. So like two problems in one.
So is the adversary also Gaussian distributed? Or
Anything.
similarly distributed?
Anything. Yeah, this can be like whatever they want. Like they know everything, they know my estimator, they know your estimator, and they will be as adversarial as possible. But something is possible even in this scenario. Of course, not with the simple mean.
The worse the contamination is, the happier you are. Because you show that you can overcome it.
No, of course, if it's too high, then if half of the points, like, if epsilon is close to 1/2, then you're screwed because.
No, with the fixed epsilon.
Yeah, but it's
You
small.
select the worst.
Yeah, you have to do some smart filtering, right? Okay, so here is the theorem. I will just state it. First, in this, 2 years ago, that's in the 2024 paper. Then actually there is an estimator, the one I will discuss in a few slides. So that does it. So what is the statement? It's relatively simple. So assume that I observe n points, right? They satisfy this hypercontractivity assumption for some p at least 4. So I need at least 4 moments of my distribution, but I'm not asking for Gaussianity or whatever. So just like, and some heavy tail student type distribution will also work with student with 5 degrees of freedom, for example, right? And then I have an estimator which depends on epsilon. So I assume that I know epsilon and I know the confidence level delta. So percentage. Then the estimator is based, of course, on the contaminated sample with tilde, such that with high probability, with probability 1 minus delta with respect to the realization of the sample, the following holds. The estimator approximates the true covariance matrix as the first term plus the second term. So the first term we're all familiar with already. This is like the sample covariance of the Gaussian case. So in some sense, you mimic this Gaussian type behavior, the sample covariance for the Gaussian, even though I only assume that I have at least 4 moments. There's no P anywhere here. And then P, and this is why I need this function kappa explicit, right? Then I have a second dependence, which is a dependence on the contamination level. So when you start contaminating, the more you contaminate, the worse this bound behaves. If epsilon is 0, then the term disappears. But if epsilon is small enough, you can easily solve this equation. Then the terms are all the same order, and you will essentially, up to multiplicative factor, estimate your covariance matrix with the same rate as if the data is clean and Gaussian, despite the fact that it's heavy-tailed and contaminated. Right, so it's a nice result. And then the second part of this result is that no estimator, so like it's a statistically optimal, can perform better up to multiplicative constant factors, right? Of course, there is some constant 1000 sitting here, and I'm saying that if you have 1/1000 of this rate cannot be improved in general, because this cannot be improved for the Gaussian, and you can also say that this dependence is also not improvable for some distributions with p moments. So there is no way you can easily bypass it. Yes.
Are you gonna give a constructive?
Yeah, it will be.
Okay.
It will be a construction. Unfortunately, it will be exponential in dimension. Yeah, so we don't have a polytime algorithm. This is a great question on how to make this polytime. So there are multiple papers trying to make it polytime. They're kind of sacrificing the rate. So you can make the statistical guarantee weaker, and then your kind of polytime, still not practical, but polytime, we are aiming for we are okay with being exponential in dimension, but we are exponential, like we are not practical, not implementable. Yeah, at least now.
So the second term on the right, that's the new thing, is like contamination tax, huh? That's what that's what you pay for having contamination.
Yeah. So I'll think about this. We'll discuss this bound a little bit more, right? So this is a universal bound. This is a nice thing. No matter how many moments the distribution has, starting from 4, it doesn't matter. It's exponential. It's a student with 11 degrees of freedom, student with 27 degrees of freedom. No matter what, the rate will be Gaussian. This kind of first term for the estimator is the same as if the data is Gaussian, and the second term is really your price for contamination, which, as I mentioned, is not avoidable.
The most surprising thing to me about this is the power that involves P on the epsilon. Is there any intuition for how you get that to work?
It's better with good P.
Bigger P helps. And with the arbitrary contamination, is there some intuition for why?
Yeah, so maybe the high level, okay, so these are two limiting cases, right? The sub-Gaussian have all the moments up to forever, almost Gaussian distribution. I pay this epsilon of epsilon, 1 over epsilon. And because epsilon is at 0, 1, of course, it's much better than having square root epsilon, right? So you are more tolerant to contamination. So the term epsilon is smaller than the square root of epsilon. Now, why there is something like this? Because in some sense, if you are heavy-tailed, like if you're a nice Gaussian, then maybe the finding the outliers, potential outliers is much easier, right? Because the distribution is more regular. Whilst you're more heavy-tailed, it's easier to put something surprisingly bad, and you will think of it as maybe it's a typical point from this heavy-tailed distribution because you only have 4 moments, but actually you're fooled by the adversary who forced you to. Maybe this is the high level. I see. But this is the magic, right? Like kind of the rate, main rate statistical does not depend on the number of moments, while the contamination depends on the number of moments. So this is it's an interesting observation was made in several papers in this literature, but this is the right race for the covariance metrics.
So P equal to infinity, you have epsilon, right? So does that make sense?
Epsilon log 1 over epsilon for sub-Gaussians.
But what happens to K?
Yeah.
Kappa. What happens to kappa?
Yeah. So the kappa, of course, it's a sub-Gaussian. So for the kappa, it has a particular form. It's square root P for sub-Gaussian distribution. So we know exactly how the higher moments are written in terms of lower moments for sub-Gaussian distributions. So therefore, we know this log 1 over epsilon exactly comes from optimizing this kappa, which is square root P.
Okay.
So there will be something even more surprising soon about this Gaussian sub-Gaussian case. But yeah, the more moments, the better.
I have a question. Your contamination model is deterministic, right? So I remember the Gauss paper, Gauss paper, under Hilbert random contamination. The epsilon part is without the log 1 over epsilon.
Yeah.
Right. So what's the relationship between this, the deterministic and the random contamination?
Yeah. So first, my model, I think, is more general than Hilbert's contamination model because you can mimic the adversarial contamination as the Hilbert's contamination. So Hilbert is just like mixture of 2 distributions. So the second thing, I'll give you this information in a few slides, so that if you have a Gaussian case, then surprisingly this log should not be there. So the log is only for sub-Gaussians,
Okay.
but it doesn't go for Gaussian. This is again unusual. If you read any of these books and concentration inequalities, they will tell you that Gaussian and sub-Gaussian for tails is almost always the same, and the theory is written for sub-Gaussians. For contamination, there's this log factor. It's really for sub-Gaussians, for some sub-Gaussians, but it doesn't appear for Gaussian. And another mystery of the Pearson diffusion. Okay, good. So I'll just give you some shortly the proof ideas. I'll not spend too much time on it, unfortunately. So the question, of course, we have to start with is the question on how to control just like the vanilla sample covariance matrix under the heavy tail assumption. Forget about the contamination. So I have this expected sample covariance minus the true covariance, which is largest eigenvalue times the effective rank over n. I would want to get this result under, say, pure assumptions with, but we don't know how to do it yet. So the best, even for the sample covariance metric, the best result we have in the literature so far is given by this matrix Bernstein or like non-conjugation inequalities, type inequalities, where you can prove that if you have only, say, 4 moments of your distribution and the distribution is bounded, like at some very high level, so you can truncate it almost for free, then the sample covariance matrix does not like reflect this Gaussian type behavior. There is an extra logarithmic factor that appears in the existing analysis of the with respect to the effective rank. So we need to bypass this. If you want to really the up to constant rate, you need to bypass any of these metrics concentration inequalities. And in order to do so, we introduce a very simple idea. So imagine that the standard difference between the sample covariance matrix and the true covariance matrix can be written as the difference between like this sum of these quadratic forms, of these quadratic expressions, minus V transpose the true covariance V, right? This is the expression. Now what I want to do, because I'm potentially heavy-tailed, right? These guys, these semantics can be pretty large. So what we do usually when we have unbounded random variables or the random variables that we can't control, we usually clip them or truncate them. So what I do, I just introduce a simple function, which is just like this, right? Of this shape. So it's the identity around 0, and then it's just a sign from -1 and +1. And then I consider a so-called trim quadratic process. So I just did the same. I picked some level lambda, and I'm now interested in computing this difference, right? Again, I just kill all the alpha in the process. I just redefine the process. I kill all the large values by introducing this clipping operator. Now, why the analysis of this clipping operator makes sense? Because imagine that you can construct a matrix, sigma, such that it minimizes, this is the computation, the hard part, it minimizes over all directions the difference between the average clipped quadratic form and this exact matrix multiplied by V from both sides. So you are not trying to find a matrix that is a sample covariance matrix, but you are trying to find the matrix that for all directions is as close as as possible to the clipped version of the quadratic process. Yeah, so this is the hard part. You can do some crazy linear programming and reduce it to some, which is exponential in dimension because you need to go through all directions. You need to replace the sphere by some net, which has an exponential size and dimension. But you can kind of, in theory, find such a matrix if it, or approximately find such a matrix. Though the complexity will be, as I promised, exponential in dimension, unfortunately. But imagine that I found such a matrix. I found a minimizer of this trimmed quadratic form among all d by dp matrices. Then this is a good candidate for my estimator, right? Because sigma hat minus sigma, like the difference, can be controlled by triangle inequality by this expression and this expression. So essentially, I added and subtracted this clipped part in the absolute value, right? I just didn't do anything smart so far. And then when I have a definition of V sigma hat as a minimizer of such expression, then the sigma hat by its construction will be less or equal than the same trim quadratic process for the true sigma. So you see, it's just like essentially a triangle inequality, which tells you that if you can cook up such a matrix, then the only thing you can, for the error bound, the only thing you have to control is to make an upper bound on this clipped quadratic process, right, where the large values are removed. Make sense? It's a very simple idea, but the nice thing is that I'll just go relatively fast from it. that even though the unclipped version of the process is hard to control, and there are many kind of open questions and conjectures about it, like how to control it optimally, or whether this matrix concentration equalities can give you the right answer. For the clipped quadratic process, you can use some other techniques that I'll explain in a second that give you exactly the Gaussian style behavior. This is maybe the key thing. If you optimize or if you pick the right level of lambda here, then you can prove that the hyperability, the difference between a clipped quadratic process and the true sigma matrix, nothing is clipped here, will be of order of this order, and this order exactly corresponds to the Gaussian type of sample covariance estimation. The only assumption I made here is the equivalence of L4 and L2 moments. I don't need 5 moments, 6 moments, etc. If you clip and plus 4 moments, you would have exactly the same behavior for clip process as if the data is countable. This is again the technical aspect of it. And I'll tell you a few words about the proof technique. So again, we're in the math department, it's a math department talk. So the nice thing is that you can try to apply some general techniques like telegram measures. Unfortunately, it works very well when you have some nice sub-Gaussian increments of the process, and you need some tails, you need some moments. But here I have very few moments, right? I have 4 moments in boundedness, so it's very hard to control the moments or the behavior of the increments of the process. So then there is another technique which is based on like some sort of Gaussian smoothing, and it does the following. We essentially put some distribution rho v, which is a product of 2 multivariate Gaussian distributions centered at any direction b. And then I write the clipped value of the quadratic process approximately as the following integral. I will write it as the Gaussian integral centered at v applied to this logarithmic function where the pair theta nu is distributed according to rho v, the product of 2 Gaussians, plus some small residual terms that I can control. So it's a very strange replacement trick which starts from the quantity I want to some scary quantity involving some Gaussian integrals centered at v. And now the idea is that if I want to control this quantity uniformly over v, because the residual term there is small, it is sufficient essentially to control this quantity uniformly over all measures, right? Over all rho v's, over all possible rho v's. And then there are some nice techniques in the literature based on the duality between the moment generating functions and the Kullback-Leibler divergence. So we don't use any uniformity with respect to vectors in the net. We instead use the uniformity with respect to these perturbation measures. So some people in machine learning call it the Pike-Bayesian method, and it is surprisingly strong in this context. Again, I cannot go into full details, but this is the core thing. So we don't use any standard telegram type generic chaining arguments. Now, how to do with p greater than 4? So this was a path to solve the problem for p equals to 4, but for p greater than 4, the dependence is harder because you have this, epsilon to the power of 1 minus 2 to the power 2 divided by p. And the estimator in this case is more difficult. Before for p equals to 4, I was just choosing a particular value of lambda, and I was minimizing these string of correct forms. Now for different v's, for different directions, I'll need to construct a different truncation level in some sense. And in order to use it, again, in the analysis, we'll need to prove this bound. So we'll go through the simple, again, we are returning back to the sample covariance. So sample covariance, either we don't know how to analyze it for case p equals to 4, or we have to analyze it when p is greater than 4. So now the question is how to prove such a bound. I have more than 4 moments of my distribution, both equals to 4, at least 4 moments of my distribution. The sample covariance is not contaminated, and I'm interested in the expected value difference between the sample covariance and the true covariance. and I want such a bound. And this question is again surprisingly difficult, and many famous people worked on related things. I'll just maybe first, okay, I'll just go with the statement, and then they'll list the names and the references. So here's another kind of intermediate result. P equals to 4 was actually relatively easy with these tricks. Now I'm in the situation where P is greater than 4, so I have more than 4 moments. And then the idea is, what we prove is the following result. If I have a greater than 4 moments, I observe yi's, I clip them at this level, and this is essentially for free. So I need an additional assumption that the norms of my vectors are not too large. So you may think of it as restrictive, but again, this assumption scales with n. So it's almost for free for most of the problems. Imagine that you have 10,000 vectors, so you just want to say that their norms are controlled by 10,000 to the power of 1/4, right? So it's something that is not very hard to request, at least in our applications. And then if n, the sample size, is larger than some constant that depends on p times the effective rank, then what we prove is that the sample covariance in expectation is approximated by the true sample covariance of xi at this desired rate. So for p equals to 4, we have one solution. For p greater than 4, we go through this result. Of course, our analysis doesn't work for p equals to 4, or this theorem doesn't work for p equals to 4, or we don't know how to prove it. So these constants around p equals to 4, they will explode to plus infinity. So but if you have 4.001, then you're fine.
So what's the relationship between CP and the kappa P?
So they're different. Like the kappa P is just it's an assumption of the hypercontractivity. Okay, there is some explicit expression. Yeah, I don't recall it, but yeah, there is something in the.
Yes, I mean, does kappa P influence CP?
Oh yeah, for sure, right? Yeah. But again, around p equals to 4, things are okay for kappa P, but they are not good for CP.
Okay.
Because we don't know how to prove it for p exactly equal to 4, so we need to be greater than 4. Again, this is of general interest, and there are some more recent papers that slightly improve this, so they don't assume that you have to truncate things. And some people wrote a version of this result where you don't truncate, but control the bound in terms of the max norm of the vectors. So there are versions of this result information. In any case, how the proof goes. So this is the famous argument we'll see in the literature. That is the first step. So if I care about the sample covariance, like this operational control, then I consider the difference between the sample covariance, the sum of covariance forms minus the expectation. And then again, the problem for the hairy tail case is that sometimes the xi's, they have a large norm, or they have the large projections into some directions. So how would I avoid it? So in order to avoid it, I need to consider two parts. So one of them is so-called Peaky part, right? It's when your values of xiv are very, very large, right? And then I just sum them up together. There shouldn't be, for any distribution, there should be too many of them that are large, if it's a reasonable distribution. But I kind of use this additively. I just take all this entire part with large coordinates and put them into one part. And there is a so-called spread part, right? Like the one where we are already familiar with, because we knew how to analyze this process from the previous slides. We knew that if you clip the process, then you're fine. Then you are essentially Gaussian under just 4 moments plus a nice clipping. So you see there are kind of 2 parts and 2 regimes. So this we already encountered, but this is something new. And yeah, so it appears that people work on it since forever, like on just bounding this exact expression, providing upper bounds for different random vectors, not necessarily Gaussian. For the Gaussian vector, it will be easy. You just there is nothing to work on. But if you slightly change the Gaussian assumption, for example, sub-exponential or log concave measures, then getting the optimal bound upper bound on this becomes quite challenging. So there are many famous people who worked on it. So I think that the technique, there is some decoupling-based technique was introduced by Jean Bourgain in '96, and then there was a major breakthrough paper by Adversarial, and Tomczak-Jagerman in 2010 that essentially analyzed this for the log concave case. So they just provided an optimal upper bound for this term for log concave measures. So log concave measures, for example, uniform on a convex body, right? Like many of these exponential distributions, like Gaussian distribution is also log concave.
So they did better than Bourgain?
Yeah, so they developed his methods to the level they
Was illegal.
yeah. No, there were many improvements. You'll see. I think he started the analysis, and then the machinery was still following his idea, but quantitative version of his result was not the sharpest, right? Like people, over the next 20 years, there was significant progress. And then I think in Michel Pellegrand's book, you can also read some control over some bounds where they discuss the control over these terms. And then he has sharper tail bounds in the log concave case. But then people start, okay, log concave is important because it's related to some algorithms in computer science on volume estimation. And it was a question of how to drop, or how to work with fewer moments. And then there was a nice paper by Mendelssohn and Poweris who provided a nice upper bound for this, assuming only at least 8 moments for the distribution for this term. And then I think the state of the art is by Tikhomir of 2018, who kind of again developed this machinery to the level where you can control at least 4 moments. So you need at least 4 moments, and we can have a nice bound, like the optimal bound, up to multiplicative constants on this term that is needed in the analysis of the sample covariation. So what we did, one part we analyzed for trimming, we analyzed with these Gaussian techniques as we mentioned. With these Gaussian perturbation techniques as we mentioned. But here we essentially extended the analysis of Tikhomir. So it was a very good line of work, and we already had some good starting point. The limitation of Tikhomir is that all these papers they considered the isotropic case where all eigenvalues of the covariance are the same. But we have this decay, and we have to be dimension free. So there was some non-trivial part as to adapt the ideas used in the later paper by Tikhomir to carefully take this Peaky part and kind of take into account the eigenvalues decreasing.
I have a question. Could
Yes.
you go back to the previous page?
Okay.
I mean the theorem page.
Okay. Mhm.
Yes. So it seems if P is larger and the things are better, right? Because we have higher moments and the tail of the distribution is lighter. But if P is large, the CP goes to infinity. So why is it?
No, it's only when P is close to. I'm saying this.
Oh, sorry about that.
The constant is nice. Like I'm just very the only sensitive regime is when you're around.
Oh, sorry.
But starting from 4.1 until forever, you're fine. You're fine.
Sorry about that.
No worries. Yeah, it's good that you asked this question. But yeah, again, there are two the two combinations. This Peaky part is analyzed extending Tikhomir's result, and the spread part is another analysis that we brought. Yeah, this gives you the.
What happens when P is equal to 1?
Then we have another separate analysis. Then we completely bypass it using this trick I provided you. So it's a relatively simple, right? I'm just scrolling back to the slide. So we're saying that we don't want to go through the quadratic process. So we'll try to work with the clipped process. And again, there is a huge linear program that solves it. And surprisingly, the spread part just doesn't appear. So there was so this entire term is missing. It's not needed because I already clipped it. I directly went into the clipping part. So we only need out of 2 terms. The one is a conjecture, But for estimator, this conjecture term is not needed. We just drop it. So again, this is we were just lucky here, but we can drop it. Okay. So I have around 10 more minutes, right? So, yeah. Cool. I think we will be done. Okay. Now there was a nice question about epsilon versus epsilon log 1 versus, right? And it's a rare case. I don't know many examples in high-dimensional statistics, but indeed there is a difference between something you see for sub-Gaussian distributions and for Gaussian distributions. Usually you have approximately the same non-asymptotic bounds. It's an exception. So the mean estimation, the covariance estimation, they're different. So it appears that you need to pay this log 1 over epsilon for at least some sub-Gaussian distributions, and you don't need to pay it for Gaussian distributions. Okay, let's recall how we can solve the multivariate Gaussian mean estimation with linear contamination epsilon. So now I'm in an isotropic case. I assume that the covariance matrix is identity. So there is a notion of Peaky's depth. It's a very nice geometric idea. So essentially what you have is you have a cloud of points. It's a generalization of the notion of the median to high dimensions. It's not clear what the median here is. But what I want to do is essentially, I'm trying to find such a point in the space in the end. So this is the definition of the Tukey's median. So there are some formulas, but then I can explain what's going on. I'm trying to find such a point so that if I kind of take all sorts of half spaces passing through it, then this point is so that among all the rotations of this half space, I contain like as many points as possible. So you don't want to be here, right? Because this half space will contain 0 points. But if you put it somewhere in the center, that no matter how you rotate it around this star, you will have at least 30% of points. And the Tukey median is essentially the point that for all rotations around, for all possible half spaces that passing through it, will contain at least as many points as possible. Right? So that's kind of the definition of the center. And the Tukey's median is a Gaussian element. This is so this is a theorem of Chen, Gao, and Ren. I think this is the result we mentioned. That is telling the following: if I have a contaminated sample of independent isotropic Gaussian vectors, so isotropic means that this is forbidden, right? Lambda 1 is equal to lambda d. So all the eigenvalues are the same. If I have this similar all the eigenvalues are the same, then the Tukey's median provides me the following rate of convergence, like Tukey median minus the true mean. So it's not a covariance; it's a sample mean estimation problem. Is optimal to pick up for the dimension of the sample size plus linearness. So the linearity is here. There's no log 1 version. It really uses the Gaussianity. At the same time, the rate is optimal up to multiplicative constant factors. The same paper provided the matching lower bounds. But the problem is this dimension. So the dimension, I want to take into account this decaying eigenvalues. How to get how to get to the desired bound? So when we try to study this estimator, we realize that there are some negative results. That Tukey median, just to be well defined, you need at least n should be at least dimension to make all the things work nicely. And there are also technical complications. So we don't know. We know that Tukey median can perform well when there is no contamination and n is large enough, but we don't know how to prove that it really achieves the optimal rate. Okay, maybe it's a limitation of our analysis, but I know that several groups tried it, and nobody proved yet that the Tukey's median, the classical estimator, also works with the general covariance matrix. So instead, we use some another tool also motivated by these Gaussian perturbation tricks we use in the proof for the trimmed quadratic process. But here is the estimator. Again, the estimator will be it will be a linear program that will have the number of constraints that is exponential in dimension. The question of how to run it in polytime is open, and the same is actually for 2K median, right? Like, we know it's NP hard in full generality. So this high dimensional mean estimation conversions, they're hard, like computationally. But at least we can achieve the optimal rates of convergence. So here is the idea. So we will be considering certain medians, but these medians will require an additional thing which will be related to so-called smoothing. So here is the thing. Assume that you observe any vectors, they can be fixed, like x1, etc., xn in R&D, and we construct for these vectors kind of a noise vector which is Gaussian, with zero mean, and whose covariance matrix is proportional to the gram matrix. So you just give me a collection of vectors, and I can construct, if I pick beta properly, I can construct such a measure. Now, what I do next is I introduce the following estimator. So for any, it's called the smooth median or smooth medius. For any direction v, any projection, I project my vectors onto this direction. Then I add this Gaussian noise to each individual projection, psi1, etc., psi_n. Then I take the median of these values, so the median values is a sample median, and then I average over all of these noises. So it's like a double, it's a very strange construction. So we just project, the median is a good idea, but for the median we cannot prove what we needed, then we needed a little perturbation, the Gaussian perturbation. So, and the final estimator for the contaminated sample is as follows. It's a point, it's a very similar definition to the 2K's median, right? It's a point such that for all half spaces, it maximizes the number of points that, kind of belong to the worst half space. And this is a geometric analog where instead of counting, I'm using the smooth median projection. So it's such a point such that for all directions, the projected value of the smooth median on this direction is as close to the linear form with respect to this center. Again, it just, if you've never seen anything like this, it blows, it can blow your mind, but it's at a high level, it's really related to this idea of the 2K median, right? It's something that works for all directions, for all half spaces simultaneously. It should be good for all of them. So this is the same sort of uniformity, but the approximations are made by the smooth median. Yeah. And this is also linear. You can do the in time, approximated in time that is exponential, like it will be n to the power of d, or maybe n to the power of 100. Right? Dimension 1, there will be some, or dimension 3, there will be some all the time in the number in the input algorithm.
If your covariance matrix is low rank, then it will be exponential in rank, assuming.
For the bound, you will see it will be nice. It will not the bound will not incorporate any dimension inside, like to be dimension 3 statistical bound. But for the computations, you still need to go through the entire sphere. So you see, D appears in the definition of the estimator, but D will not appear in the bound. And it's a bit esoteric and abstract, but this works.
How do you compute this smooth median in practice?
It's not hard because for a given direction, it's easy because you just have the following, right? You have a Gaussian measure, the median is nice, and then you can just use a Monte Carlo sample.
Oh, Monte Carlo.
Okay. So kind of point, and then you can just even approximate, if you are again happy with exponentially dimensional complexity, then you can union bound Monte Carlos over the entire net that represents the full sphere. Okay. Yeah. Again, I'm not saying that you can implement this, at least like, hypothetically, with supercomputer in dimension 2, you can compute it. Right? Maybe, I'm not sure, maybe it's like something like n to the power of 100 or whatever. Like, it will be a hard linear program in this case. But at least it's theoretically implementable. Right, so I'm almost there. I'll just mention the result, right? The result is separate and it's different from this chain and Chao-Gao and Ren's result, it gives you the optimal rate for the, like we proved that this smooth median gives you exactly the correct rate for general covariance. So the Tukey median gives you the optimal rate for mean estimation when you have isotropic covariance metrics. And here there's no assumption of the covariance metrics, like any covariance metrics. And the dependence is not on the dimension, but on the effective rank. So again, I fully incorporate information about the decaying eigenvalues. Yeah.
So what's the breakpoint of your method?
Yeah,
Computing.
It's actually approaching one half. It can be as close to
Okay.
yeah. So it's because of the median. So median is very close to, it's arbitrarily close to.
Oh yes.
Yeah, this is essentially the same. So
Okay.
the breakdown point is good here, but yeah, the computational is maybe even worse than for Tukey. Because for Tukey median, at least there are some heuristics and approximations. For here we don't know them.
Yes.
And what is nice, I think, as the previous paper on the Tukey median, like this 2018 paper, made a nice reduction, like made a nice step from mean estimation to the covariance estimation. We also used with the same tricks with some slightly more involved estimator, the generalization to the Gaussian case. So we proved that if the data is Gaussian, so it's not even P plus infinity, it's even more. I really use the Gaussianity, I really use the density in the analysis. Then we can, based on the similar ideas, we can construct a sample covariance estimator such that the dependence here is linear in epsilon. So the log 1 of epsilon disappears, but the Gaussianity is due crucially reduced. Yeah, I think that's it. I will just make some conclusion and open problem section. So we build the, if we focus on the covariance, right? We build a covariance estimator that achieves this sort of rate depending on how many moments you have. This is again the Gaussian style behavior, plus this depends on contamination level, where P is the number of moments in the hypercontractivity. So if you assume that you have 23 moments, then you know the rate of convergence. And this doesn't propagate all the way up to the Gaussian case, because in the Gaussian case, P is equal to plus infinity, but you will pay for kappa, so it will give you an extra log factor. What is nice is that in the Gaussian case, there is another estimator. There is no universality, so we need to use different estimator here and here. But there's another estimator that still achieves you the optimal linear dependence on epsilon. And of course, the main question here is like how to make it computation. So maybe computation efficient is even too ambitious. Now, even polytime approximations would be nice, like not practical, but something that you can say this is a polynomial algorithm for computing this. Yeah, I think that's it. Thank you very much.
Yes, we have an estimator for the covariance matrix. Then we want to use it in estimate the leading eigenspace, right? But if